So welcome to my talk. So I'm working as a data scientist at Blue Yonder. So we develop and run software for supply chain applications. And of course, forecasting is a really important thing of what we do. So we do build a lot of models, and we want to know, are these good models? Are they working well? And for that, we've developed a method that we call uncertainty-aware model rating, in which we don't pretend to know everything and that the model can tell you with certainty what will happen, but we manage the uncertainty. So we try to know what we don't know. So we want to go beyond the description of a model, but we want to provide some uncertainty-aware ratings. So what's the difference between a description and a rating? Take something completely different for a moment, the sandwich, and ask, is this a healthy sandwich? The first thing that you might do is to look at the chemical composition of the sandwich. So how many calories are there, how much salt, how many fibers, saturated fats, and all these things. Now, to interpret this, you either need a lot of human experience, or maybe you are very much into food and nutrition and you know what all that means, or some education. But typically, this is not really answering the question, is this a healthy sandwich? This is why in many places you will find these ratings on the food. So in the EU, we have this Nutri-Score, but it also exists in other countries that will rate the nutritional value, that will interpret it and judge it and put it into a context. So this is meant to be interpreted by a much wider audience. It's a qualitative rating, that lay people should understand, like, the salad has an A, is good for me, and the donut has an E, and I shouldn't eat too many of them. Now, that's the difference between a description and a rating. But of course, we are not into nutrition here. We are at PyData. So we are talking about models, about predictions and actuals. And also here we ask the question, is this a good model? So the first thing that we do is to compute the accuracy KPIs that are similar to a chemical composition, like you will get a mean absolute percentage error, a relative mean absolute error, or mean absolute error that have certain values. But again, to interpret these, you need a lot of human experience. So maybe you're into forecasting for the last 5 years or so, or you have a PhD in statistics. But this is not accessible by a wide audience. So we have developed a forecast rating that is interpretable by lay people that will give you a rating between 100% in the bluish area. That means that's a perfect forecast, down to 0% that tells you this is a horrible forecast. And this is what I would like to present you today. So what are the use cases? In the first place, you want to compare different models. So you're into model comparison. So maybe you have a time series model, a machine learning model. You want to know whether the shift in accuracy is just a very small step or a big step. You want to have it on a scale that tells you where you are. But also, if you are focusing on one model, you want to compare data sets. So assume you went for the machine learning model and you want to improve it. You want to know, should you focus on the shoes or on the fruit if you're a retailer? You might even want to do some hybrid comparisons. So you already have the machine learning model live for the shoes and the time series model for the fruit, and you think, okay, could you maybe switch or so? So you want also to compare in a cross way. Now, why is this a problem at all? I mean, why are people not immediately happy with a common answer? This is because there's quite a divide between practitioners in industry, so how things are being done, and statisticians that tell us how things should be done. Take, for example, the forecast of 5 t-shirts. The practitioner will interpret this in an ideal deterministic world and say, well, forecasted demand of 5 t-shirts means 5 t-shirts will be sold. I will not sell 4 t-shirts. I will not sell 6 t-shirts. The probability is 100% to sell 5 t-shirts. The statistician will interpret this as, well, on average, 5 t-shirts will be sold, and I will see a distribution, maybe the Poisson distribution that we'll use in this talk, and so on. The practitioner wants the forecast to be ideal, or the best forecast means that the relative mean absolute error just matches 0. So if I take my prediction, I subtract my actual, I take the absolute value here, and if I think I live in a deterministic world and I have a perfect forecast, then 0 should be achievable. The statistician will say the best forecast is the sharpest, least uncertain one, as long as it is calibrated. So by sharp, they mean it's a very narrow distribution, and calibration means that the reality actually behaves like the distribution predicts. Now, this is not just two different languages, it also leads to very different practices. In industry, many people use mean absolute percentage error, while statisticians have been telling us that this is a bad thing to do for the last 10 years or so. So today I want to present a rating that uses business relevant metrics, but in an uncertainty aware way. So by that, I'm trying to please both. I'm trying to please the practitioners and the statisticians that hopefully both say, yeah, that kind of makes sense. So we'll build an evaluation procedure that takes many predictions and many actuals and will produce some results, some rating, which is really qualitative, which will tell you have a fantastic model, you have an okay model, or you have a really bad model. So we need some data to work on, and I've used the M5 competition data from Kaggle, which you can download here, and we're looking at the validation period in April and May 2016. So in the first part, I will now gauge the evaluation procedure on a perfect model. So we will start with the result perfect, we will build a perfect model, and then see what this evaluation procedure should do to really give us perfect. We will then see how to define the green, dark green, yellow, and so on areas, and apply this on some more realistic models from the M5 competition. So let's start with fabricating a perfect prediction, and I call this a post-diction because we just use the actuals in sample to build a perfect model. We are applying a method called expectation maximization under the Poisson assumption, and in a way you can think of it as intelligent cheating. I mean, we know what are the actuals. We don't set each individual prediction to match the actual, but we put a little bit of noise just to make it plausible. So it's kind of smart cheating. And if you cut on the different post-dictions that we make with this procedure here, you find a distribution of the sales that matches really, really well the predicted probability. So if I cut on post-diction close to 2, I expect to see the red distribution and I see the blue distribution. Same for 6 and for 10. So we've built a post-diction, a fantastic, perfect model that we know must rate as being perfect in this procedure. So let's evaluate it. The first thing that you would do is you will evaluate the bias, and we constructed a perfect model, so it's not too surprising that there is no bias. The next thing that we would do is we compute the noise, and for that we use the relative mean absolute error, for which we need to take the median of our prediction, because our prediction is a Poisson prediction, and we find this value here of 41%. Now, if you go with the value 41% of RMAE to a practitioner, they would typically tell you, oh, that's a lot of noise. Isn't that a very poor model? Let's break it down by department. Let's try to find out where that noise comes from. And if you do this for 3 departments that we focus on here, you would find these numbers here. So Hobbies 2 has an RMAE of 76%, Household 1 of 49%, and Foods 3 of 37%. So you find quite different values of RMAE. And if you look at the mean sales, you see that it's correlated to the velocities of the selling rate in the departments. So the bias is still fantastic in these different departments, but somehow the noise seems to depend on the average sales. But again, our prediction, that was built in sample. I mean, it's by definition somehow a perfect model. So where is this coming from? We can also plot it and see, okay, there's a clear relation between our velocity and our relative mean absolute error. So probably I just can't do a direct comparison. But how should I then compare this? Because I still want to ask the question, if I had a real model, should I invest my time in Hobbies 2, in Household 1, or in Foods 3? And for that, we find that this method is really, really helpful, is to bucket all the predictions and actuals by the prediction value. And we'll use logarithmically spaced buckets because this will give you some more or less equal population in the different buckets here. So between predictions of 0.1 per day to 100 per day. And you can do this quite easily in Python and define a column rounded logarithm of the prediction. And now we just do a group by this new column here, and we will evaluate everything stratified by these buckets. So the first thing that we can do is we can look at the bias per bucket. We already know there's a very good or lack of bias overall. There's a very good lack of bias for each department, but we also see in this plot here that for each bucket that's defined by its mean prediction, so here we have a bucket with predictions around 1, predictions around 10, around 100, the mean prediction divided by the mean sales per bucket is very close to 1. So this is where we want it to be. So we are unbiased even in each bucket of predictions. The predictions of 100 are as unbiased as the prediction of 0.1. Now that's not too surprising. It becomes more interesting if we now look at RMAE in this per bucket view. And now we understand where these overall means come from, because for each individual bucket, the three departments perform equally well. So predictions of around 1 are of the same quality for foods 3, for hobbies 2, and for household 1. Just that for hobbies, I have more predictions that come from the left-hand side, from the slow movers, than for foods 3, where I have more predictions that are populating the buckets on the right-hand side. So if I do the overall mean, it's clear that foods 3 has to be more on the right lower corner, while hobbies 2 is more on the upper left corner. The nice thing is we can even find some semi-analytic expression for where perfect is in the space of prediction and relative mean absolute error, and understand where this comes from, because the Poisson distribution is simply more broad for the slow movers than for the fast movers. So we can define what is a perfect model. A perfect model is one where the achieved KPIs just lie on this best possible line. And finite relative mean absolute error has to be rated as absolutely perfect. Now, this is not what you will see with a real model. With a real model, you will not touch this line. You will be a bit above. And we can now assume that, say, for one prediction bucket, like, say, predictions around 10, you found some agreement with all stakeholders what you still call a good rating. Maybe you're here at a RME of 45%, an okayish rating at 60% RME. So you would gain some understanding of what is a good forecast for one prediction. But the question now arises, how does this scale? How does good scale? So do I have to redo all this understanding what is good, what is okay, and so on for every bucket? I mean, that would be a lot of work and not very nice. And indeed, we can find a systematic way for this scaling. Now, scaling of a perfect model is quite straightforward. Take the Poisson prediction of 10 that has a variance of 10, RME of 25%. There's one way to scale it up to a prediction of 100, and the variance just scales like the mean. So it's relatively more narrow. The variance for a prediction of 100, it's also 100. The RME goes down to 8%. So there's nothing unclear here, or that we would need to choose. For an imperfect forecast, it's not that easy, because now we have a higher variance. So say this is what we call a good prediction, has a variance of 35, an RME of 46%. And when we scale up the prediction by a factor of 10, what happens to the variance? We can, in general, write the variance as the Poisson part, that's a prediction, plus some over-dispersion, that's a factor times the prediction itself to the power of some exponent. So the Poisson case, the ideal case, is that factor is 0, but in general, we will have to live with some over-dispersion here. And the question arises, what should that exponent be? That exponent could be linear. Then we would end up with the green curve for prediction 100. It could be quadratic. Then we end up with this broad blue prediction here, or something in between, like exponent 1.5. But this would leave us with very different variances at prediction 100 and with very different RMEs. So in the prediction per bucket and RME panel, it's like we have to choose between these different ways of scaling. And we already see from the eye that quadratic dispersion is somehow too pessimistic on the fast sellers. I mean, it tells me that for a prediction of 1,000, I still have to live with 40% RME. That's quite a lot. The green curve here is coming very close to the black one for the fast movers. So this one's too optimistic. And it also makes sense if you think of what these scaling laws would mean, because quadratic scaling means that you assume that all the systematic errors that you have in the slow movers will add up coherently and reinforce each other when you go to the fast movers. Linear means that all these systematic errors cancel each other. So you have no systematic errors that prevail when you get to the fast movers. This is why the green line comes very close to the black line. So we know that in reality, it has to be something in between. Parts of the noise between fast and slow sellers will be correlated, part of it will not be correlated, and already by eye, it somehow makes sense to have this intermediate case. So we can now define a rating for the models like this. We know what is the best possible performance. That's the Poisson distribution that's giving us this blue line here. Then we define a model rating for one prediction, for example, 10, and we find an agreement what is good, what is okay, and what is insufficient for a prediction of 10. And then we can scale these reference values across the board to have this, this overall rating. Now that we've defined how to rate models, let's apply this on a few models on the M5 competition. We're keeping this post-diction as a reference. We then use a naive one-day ahead model where today's prediction is just yesterday's sales. So it's a very simple model. We have a light GBM implementation that also uses some additional features, and a simple 28 days model that has a weekday profile but averages the 28 days mean per product. So let's see how these models perform. So first of all, we start again with the overall bias, and we see that all models show quite little bias. So simple 28 days has a little bit negative bias. The average prediction is a bit lower than the average sales, but apart from that, the bias has no big difference here. And if we go into this bucket-wise representation, we see a much richer picture. So here we have, again, the mean prediction per bucket on the x-axis and the mean prediction divided by mean sales per bucket on the y-axis. And I have put some colors to give you some visual indication whether something is very good when you're very close to 1 or absolutely unacceptable when you have a bias that's more than a factor of 4. So our post-diction here is absolutely perfect apart from some statistical limitations. So the red bubbles, they all lie nicely very close to 1. That's not too surprising. The naive one-day ahead model is overall perfectly unbiased, but we see a regression to the mean effect. The large predictions that come after days with surprisingly many sales are typically over predictions. So this is why we are here in the over predicting range here. The small predictions, so the prediction 0 that are shifted to 0.01 here, that's typically an under prediction because that day on which the product was not sold, that might just have been bad luck. So we see that an overall bias can still come with a quite bad bias per prediction bucket. The simple 28 days model improves quite a lot with respect to this naive model. So you see how all these bubbles are pushed towards the ideal. But the light GBM model is still better. I mean, you can hardly see the blue bubbles here because they're hidden by the red ones. So they are in the perfect range. And only for the very small predictions, we have some under forecast. And now we can do the same plot, but for RMAE. And we see that even though the models don't know about the scaling property, they all respect it. So we actually used the naive one day ahead to gauge our models. We said if you have such a model, that should be rated as something between fair and insufficient. So it's no surprise that the orange bubbles are between fair and insufficient, but this allows us to make a very clear separation of the models here. We see the post-diction is perfect, light GBM is in the good range, in this dark green range, simple 28 days is in the yellow range. And not only is light GBM better than simple 28 days, light GBM is better for each individual prediction bucket. So it's better all across the board and respecting this scaling property with exponent 1.5. Now, this is I really like this visual representation, but sometimes we need to summarize it into some numbers to give an overall rating because you don't have the time to go through these plots. And you can weight each bucket by the maximum of total sales or total prediction in the bucket, and then ask, okay, is it in the fair range? Is it in the insufficient range, in the unacceptable range, and so on, and make an overall mean here. And this is what would come out. We would have a noise rating of close to 100% for our post-diction. That's not very surprising. The naive one day ahead model is rated with 41, which is rather mediocre. Simple 28 days is in the okay range, and light GBM is then in the good range. Now, probably you want to then use light GBM because that's the model, the best model here, and then you want to improve it. So you are asking the question, which department has a potential for improvement? So you would redo these plots here now for different departments. So we are doing data set comparison. And what you find is that household 1 is a bit better than foods 3 for each prediction bucket here, just not for that one, but for most, it's a bit better. And this is also why the noise rating of household 1, based on that picture here, is better than the one for foods 3. So we see that we are already better in household 1 than in foods 3, even though the RMAE is telling us a different picture. It's telling us household 1 has a higher RMAE than foods 3. But the scaling awareness tells us the different story, and will tell us, well, in food 3, you might be able to improve a little bit, but household 1 is already quite close to the ideal. So when and how should you use uncertainty-aware model rating? So the most important application is when you compare different data sets on the same model. When you ask, should I focus on the shoes? Should I focus on grocery also? Because there you will fall into the scaling problem. So uncertainty awareness in some way is really a must if you're on this vertical line here. If you compare models on the same data set, uncertainty awareness remains quite helpful to really understand how is that model better than the other model. But very much in general, I mean, don't judge slow and fast movers together, because slow movers and fast movers are just different things. We typically group data into buckets of similar prediction and evaluate all those separately and get these pictures here. For rating, think about what is the process that you're modeling and what would be the best model. How would it perform? I mean, in retail, the best possible model is often the Poisson distribution. In a different industry, it will maybe be a different distribution, but this should define the perfect place. And then you can select some simple model to gauge the scale here, to define where does red begin. Then compute these business metrics under the distribution assumption. So to be realistic, to understand like where could you possibly be with a certain metric. And always consider at least 2 metrics. Bias and noise alone are insufficient. So at least those 2, and maybe even others. I'm happy to continue the conversation on talks discussion, but if there are questions now, of course, I'd be happy to answer them here.
So there is a interesting question asked in the channel. It says, would you be able to recommend some basic educational materials for statistics?
Maybe I can share a few links, but definitely, I mean, just so for retail, it's super important to get some impression of how the Poisson distribution just looks like. And so negative binomial distributions, Poisson distribution, how they're related, and all these things. Let me look for some links, and I'll share them in the channel.
Great. And I think that's like the all questions we have on deck. Do you have anything else you want to be like sharing with us throughout the presentation? Oh, also one more. How can we estimate the ideal models for things like ranking? From Steve saying.
So it's a question like which would be the ideal distribution?
I think what he's trying to ask is like, how would we be able to evaluate throughout different models for, like, let's say you're building a recommendation system, right? How would you be, what sort of like model or starting models you would be using for that?
Okay, for recommendation systems, then so maybe I would build a toy system where I would say that's the very best but still realistic model that I could possibly achieve, because there will be some sources of uncertainty that I will never control. So so there will be some upper limit on what I can do. And using that maybe as a reference model will be helpful. Indeed, this is often a difficult question. So retail is easy in that part because we just see that Poisson is the best case, and it's quite universal. So it's quite well defined. In other industries, you might need to reflect, okay, what is the process that I'm trying to model? What is my assumption that I make when I do my model here, and what could I possibly expect in the very best case?
Gotcha. And yep, I think that's all questions we have for now. And if you wish to continue or wrap up a bit.
I have, so we have some time left.
Yeah, technically we have about like 5 minutes left. So if there's anything you want to keep going through, or if you want to
then let me then take the opportunity to show one slide that I kicked out.
Sure.
Because I insinuated that there's a divide about whether to use our maybe or not. So let me take sides in that divide. So can you see my screen again?
Yeah, I can add that to the stream.
Yeah, so I insinuated that there's quite a controversy. Is maybe a good metric for count forecasts, and like this uncertainty-aware model rating that I presented, I applied it here to RMEE so far, but you can also apply it to MAPI and see what does the best MAPI look like as a function of your prediction. So MAPI is your prediction minus the actual divided by the actual for each actual, which means that if my actual is 0, I have to remove that data point because I cannot divide by 0. So I'm removing part of my data, which is also the reason why for very small predictions, I can have very, very good maybes, because then my point estimator, so my best guess, is just 1. And since the overall probability to sell something is quite low, this best guess will be very good. And this is why the best maybe goes to 0 when I go to the left. Then it goes up, and then it goes down again because the Poisson distribution becomes small in the limits of very large numbers. So I have this very complicated shape here that makes it very hard to judge, okay, you have a MAPI value of 30%. So what does it mean? 30% for this bucket is good, 30% for super slow movers or super fast movers is pretty bad. But it becomes even more complex when you add these lines that tell you what is the same quality, because there's a big asymmetry in MAPI that for super slow movers, noise has very little impact. It just increases a little bit the probability to see some large outcomes, but the relative error for under predictions is bounded by 100%, because so if you predict 0, the worst absolute percentage error that you can get is 100%. And if you're on the right-hand side, you will sometimes overpredict, but the worst absolute percentage error that you get for overpredictions is unbounded. And this is why you have this explosion of maybe for these moderate values. So if you evaluate maybe and you get very different values and you get values that seem very dramatic and catastrophic, I mean, bear this in mind. Maybe just behaves in a really odd way, and that method is showing it that a good model can have a 70% maybe for the mid movers.
Well, I think we can pick up one last question from the channel from Emiliano. I'm not sure if that's how I pronounce it, but the question is about, like, wouldn't a Bayesian approach actually incorporate the uncertainty by calculating the posterior distribution of the data?
So the this expectation maximization is very Bayesian. So we try to then get to a prior distribution for the rates, and indeed, so far we always did a bucketing per prediction, and you might ask, okay, why don't we bucket per outcome? And if you bucket by outcome, then you have to solve all the question about what's the prior of the prediction and what is the expected outcome, and there you would probably apply Bayesian methods.